Welcome. So, in this session, we are going to be covering hyperparameter tuning. We're going to be looking at hyperparameter optimization. And hyperparameter optimization is our way of, we train a base model normally, and that's what we've been seeing in the previous classes. We train a base model. But the first instance of this model that we train, they are not always the best version, especially when we use algorithms that have trainable hyperparameters. And what do I mean by that? For example, for something like random forest, if you change values like n estimators, like max depth, like criterion, these changes can impact the performance of your model, can either make the model good or bad. So our job is to actually find the combination of hyperparameters that makes the model better. And within a grid, there is always going to be some set of hyperparameters that does that maximizes what we are trying to actually achieve. In the case of classification, those combination of hyperparameters will give us higher score on our metrics. For example, let's say F1 score. And in the case of regression, they are going to give us the lowest possible RMSE on the test set. So, firstly, let's start by importing everything that we need. Then we can get deep into all of this. So, I'm going to just do the usual import pandas as PD. Then we import NumPy also. Then we are going to from scikit-learn. So let's just use decision trees for everything we're going to be doing from scikit-learn.tree. I'm going to import decision tree. Let's just start off with a regression problem. Then we can see we can import plotly so that we use the practice dataset from plotly. So we say import plotly dot express as px. Then we can come here, and what other thing do we need? We are going to say from sklearn dot preprocessing. We are going to need to preprocess, and you've seen this a few times in the last class. So import scalar. You can always say there is min-max scalar, there is robust scalar. Depends on what you want to use. Probably in this course, let's use robust scalar. Then encoder also. There is also one not encoder, so probably should use that in this example. Then yeah, that is everything I go. Let's get from sklearn dot model selection. We import k-fold. Actually, let's just import cross-val score. Let's do both and k-fold also. All right. So the modules that we're going to be needing for hyperparameter tuning itself, we have not imported them. So there's GridSearch. In fact, there are several ways of doing hyperparameter optimization, and the first one that we're going to be looking at is GridSearch. So GridSearch, and I'm going to explain to you what that means as we get in. So yeah, um, now so since this one that we are working on right now, the one that we are writing uses, this is not the correct way of spelling search. Grid search. Perfect. So since this example is going to use GridSearch, we are going to come to this place where we have sklearn.model selection, and we are going to include GridSearchCV. Then we can run this whole thing. So the next thing is to load the data set. And how do we do that? Very easy. We're going to say data equals, we're going to be using that sample dataset from Plotly, that tips dataset. And if you check it out, I think we've used it in some previous class, some previous session. So we see we have all of these: total bill, sex, smoker, tip. Okay, so we want to use all of these to predict the tip. So our target in this case, what we are trying to predict in this case is the tip. Great. So all we need to do now is come here and get, you see, x equals data dot drop, and we see columns equals tip. Then that is not right, should be in quote, and y is going to be equals to data of tip. Yeah, like that. So we have our x and our y, and the next thing we are going to do is we are going to actually split x and y into train and test set. You already know how to do all of this. So you're going to say, and this is just for really training the base model also. But it is also good practice that we do all of those search and everything on just the X train. So here's what I'm going to do. I'm going to say X train, comma, uh, X test, Y train, Y test. That's going to be train test split, and X comma Y and test underscore size. Did we import train test split? No, we did not. We need to come here and say train test split. So test size is going to be equals to 0.2 and random state 23. Great. So the next thing to do now is to actually, if we do this, I think if I should check what X train looks like now. Right, so these are X train. So what we need to do is to actually pre-process this data. You know, we encode the categorical variables, and we um do what? We scale the numeric variables. So we can say pre-process the data. So instead of, because we've split our data, one thing we could do is we could create a function and say def encode, but encode and scale, and that's going to like take a lot of writing manually, because we still need to track majority of the things that we do inside X-train so that we can propagate that to the X test. But we don't have to write that by ourselves manually. We can use column transformer. There is something from sklearn called column transformer. So we can say sklearn.compose import, yes, column transformer. So we can use this particular module to do some things on the training set, like do something on the training set and then propagate that to the test set, just the same way you use scalar.feed, then scalar.transform on the X test. So how does that work? First thing is we need to get our numeric columns. The columns we want to perform numeric operation on. So I can say numeric columns equals x underscore train, and do x underscore train dot select the types, or we could just do x dot select the types, and we can go include, and we just get a list because both integer, I want to include both integer and float. Then all we need is their column names. You can just say dot columns. And if we come here and check out numeric columns, we are going to have total bill and size. Those are the only two numeric columns. You can come here and say categorical columns, and that is going to be select the types like this, and we can check out categorical columns. So it's a sex, smoker, daytime. So we've grabbed the columns that we need. So the next thing that we want to do is actually init the preprocessors. Like we have two preprocessors that I want to use, and number one is encoder. So we say encoder equals more not encoder, and we are going to pass in a parameter for it to handle unknown. So whenever it sees unknown value, it should not throw error. It should just ignore it. And we can say scalar, and that is going to be robust scalar. Perfect. So the next thing for us to do is to set up the pre-processing pipeline. So how do we do that? We are going to call, let's call it preprocessor, pre-processor, and we are going to use that column transformer, sorry, that we created at the top. And what you just need to pass in is transformer equals, then we can open up a list, and inside that list we can pass in a tuple of each of the things I want to do. So firstly, we want to perform some numeric operation using scalar, and we want to perform it on numeric underscore columns. Very easy. And second one is going to be uh, categorical. It's going to be named categorical, and it is encoder objects that I want to use to perform that. I want to perform it on categorical columns. And that's everything. And the next thing to do is to actually fit and transform and transform um, train and test set. So how do we do that? We are going to say x underscore train underscore transformed. Let's say x underscore train underscore trans. Let's just say transformed is going to be equals to preprocessor dot fit underscore transform, and what we are doing is x underscore train. Then we're going to say x underscore test underscore transformed. That is going to be equals to preprocessor dot fit no dot transform, just transform. So you fit transform your x train, and you just um propagate that to the x test. What's the issue here? Right. So right, this is going to return a numpy array. So if you are both of these, they are going to return numpy array. So if you are interested, you can actually just convert them back to pandas data frame. I know some people like to really um see pandas data frames every time. So you can go like columns equals x underscore train dot columns like this. All right. So you can come here and say x underscore train. I mean, you could probably do it just at a go here and go like pd dot data frame, and you can do data equals this, and you can say columns equals columns like this, right? Then you can do the same thing here. Now from here, I'm just going to copy from here, paste it here, pd dot data frame data equals this, and columns also is going to be equals to columns. Or you can just do it in a new line. So if you check X string now, not X string actually. Oh, we have an error. I think we have an error coming up. It says shape of past value is 195 by 12. Indices imply 195 by 6. So let's see what the problem is. On what line? So it is this line where we are doing transformation actually. So the first thing I'm going to do is I'm going to Control Z all of this so that we have what we already have earlier and see if it fixes our problem. So X train transformed. I'm just going to, this doesn't really matter, but I'm still going to remove it. So let's see if we get, I'm going to start from here again, run this. So let's see if we get, um, if it runs, okay, it runs. It ran rather. So if we do X train transformed, that is going to give us this array. So, and this is the array that we are trying to turn to a pandas data frame. So let me see what the problem is. So if we do pd dot data frame, then we can go data equals this, and columns equals, let's come to the top here and do columns equals X string dot columns. We can maybe list it to just be extra sure. List it like this. Perfect. You can say columns equals columns and close that. Okay. So what we are going to do is this X train underscore transform dot shape. Oh, that's true. That's true. That's true. That's true. We are using, I've forgotten. We are using one not encoder. We are using what? One not encoder. This. So whenever you are using one not encoder, what actually happens is, for example, in let me show you. In X, let me show you X dot head. So in I'm sorry. In the case of X here, so for example, when one not encoder, if one not encoder wants to encode this sex here, it is going to give female a new row, a new column, male also a new column. So it's kind of like this. If you do pd dot get dummies, I think there is, yeah, there is a pandas equivalent for it for get dummies. So if I pass in my data as X of let's say smoker, to just show you what is smoker, comma sex, just so you see what I mean. Yeah, I think this should be smoker is supposed to be smoker. Right. So here now, this is how one not encoding. This is what one not encoding does. I think there's a way for us to return floats. Let's quickly check. There's a way for us to force it to return float. Let's check, let's check, let's check. Let's check, let's check, let's check. The type, okay, say the type equals float. Let's see. Perfect. So in this case now, we are saying this operation that you are looking at currently is one not encoding. And what this is what we want not encoded. just these two columns here. These two columns here. Let me add that here. So you see, this data set here has smoker and sex, just two columns. But when we're done with one of the encoding, it has how many columns? One, two, three, four. Because this smoker is going to create a new column for it. And there's going to be a column for smoker yes and smoker no. So this is smoker no, this is smoker yes. Then there's going to be one for sex male, sex male. So, and this is the same reason why we have this problem. And that's why I won't even bother like converting into a pandas data frame. Why? Because we've one not encoded. Initially, we have 6 categorical variables. And after all of the encoding, that's ballooned up to 12. Right? So that is the problem in this case. So I'm just going to leave it. Unless you want to be tracking how each of the columns, how it happens, like all of the transformation that happen, which is going to really be a waste of time. And if you are not comfortable with that, you can just use label encoder. So yeah, that is the explanation for why that is. But everything works perfectly. Now, the next thing for us to do is to train a base model. So we can call it base underscore model. As a base underscore model, let me run this. Base underscore model equals decision tree regressor. And we are just, the only thing we are passing in is random state. And we're going to say base underscore model dot fit x underscore train transformed x underscore test. I'm sorry, x underscore train transform y train. And then we can say base underscore model and say test underscore preds base underscore test underscore preds. That is going to be equals to base underscore model dot predict y test. So if we run that, we can get our base metrics, get base metrics. And how do we do that? We are going to use F1 score. I don't think we're going to use RMSE. So I don't think we have that. We're going to say from scikit-learn dot metrics import root mean squared error. So we come here, we can say that root mean squared error of y train comma base test right. So if we run that, we have an error again. It says expected two-dimensional container but got class panda series. Okay, let's check what base test spread mean, what it looks like. So we can get base underscore test spreads, base underscore test spreads. One line. Oh, this is the line that we have issue on. The place where we are doing predict y test. So it's saying that we fitted on what's that? Especially a two-dimensional container, but got class y instead. Pass the data frame containing a single row. Okay, so let's look at what y train looks like. Okay, what does y test looks like? Okay, they are both panda series, and we fitted x train transformed on y train, and we want that. So let's just maybe fit it on a numpy array dot values, then do dot values here also. See if that fixes it. And I'm guessing the problem is about. Since expected 2D array got 1D array, okay, it might be because of our train test split. Whenever you have something like that, it is always X train X test, Y train Y. Now this looks good to me. This looks good. Here also looks. This looks good. So what's the problem? Okay, let's see what we fitted on. So we say base model dot fit X train transformed with Y train values. Okay, so if we have, let's check Y train dot values. Okay, that looks correct. Then Y test values. That looks correct. Okay, let's see. Let's see. If we call dot reshape, this guy is asking us to like set this thing to a column type, right? So you might want to do that. So I can come here and actually convert this. Where is it? Um, Hold on, please. We can convert this. Hold on. Okay. Oh, this. Oh my God. So this should take Y. Should take X test, not Y test. We are trying to predict X test. Sorry, that's my. Yeah. So right. Base test spreads. Yeah, X test. So this should work. We don't actually need these dot values. We don't. Right. So we can run this, and we still have. I think we have an error. Nope, not X test. X test transformed. Right. Oh boy. Right. So this is here. Then we can now call uh root mean squared error. And on on root mean squared error, we can do y underscore test comma base test spreads. And we see that we have an RMSE of 0.96. This does not mean 96%. It means that our RMSE model is making plus or minus 0.96 on the tips. Now that we have this, so the goal is to actually make this smaller. We want to minimize this. We want to make this RMSE smaller. So let's get to the hyperparameter tuning part. So I'm going to create a new stuff here and say this is the part where we actually do hyperparameter tuning. Actually, let's do this. Let's just call this grid search. And what I'm going to do is just name this whole thing, not grid search. Name the whole thing hyperparameter tuning. 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 Perfect. So the next thing is we can actually name this one GridSearch. Where is it? Why do we have so many of this? I'm just going to remove this like this. Perfect. So I can remove this also and run it. So now for GridSearch, the first thing that we need to do is to set up we'll set up cross validation. Cross validation. And how do we do that? The way we are going to do that is to say um, kf underscore fold is equals to k-fold, and we are going to pass in number of splits. We've learned this in the last class. So 5 shuffle is true, random state is 23, and we can go. That's really everything we need. We don't need to split it here. So um next thing for us to do whenever you're doing grid search is to set up the parameter grid. And to set up parameter grid. And the whole activity that we're trying to perform here is, for example, if you look at this base model, if we say base underscore model dot params, I think get params should be right. So currently these are all of the hyperparameters that resulted in this score, this particular score here. So these are the things I want to change. We want to find, for example, max depth is none. I want to find the value of max depth that's going to make this smaller. We want to find combined with, let's say, criterion, combined with some other things, splitter and stuff like that makes it better. So we're going to set up the parameter grid and come here. And how do we do that? We're going to say parameters or hyperparameters, or let's just say parameter grid. It's going to be a dictionary, and first one is going to be criterion, which is our first parameter, and criterion is going to be one of two things. I think squared error. You can check their documentation to find the correct ones, but just by looking at this, you probably can look at some. If you check the doc string, so for example, for criterion, we have squared error, Friedman, MSC, and absolute error, then Poisson. So I can copy all four, come here and comma paste it. So these are all of the four hyperparameters that relates with the four values that correlates with the criterion hyperparameter: squared error, Friedman, MSC, absolute error. Then next one is I'm just gonna do maybe two hyperparameters. Next one is max depth. How deep you want this thing to go, the trees to go. So I'm going to go max depth, and I can use list range. That is, it should be numbers between 2 and, let's say, 20, right? Let's say 21. So if this is everything I'm using, then I can come here now and say that. So those are just the two hyperparameters I want to search for. So I can come here and say grid underscore model is going to be equals to GridSearchCV, and first thing that goes inside is the estimator, if I'm correct. Yeah, I'm correct. So estimator, and estimator is going to be our base model. So we can come here. We already have it at the top here. Where is it? This particular base model here. I can say estimator equals base model. Or if you want, you can initialize a new one. You can say regressor. I feel like that's going to be the best idea. You can say regressor equals decision tree regressor and set random states to 23. So instead of saying estimator equals base model, you can go estimator equals regressor. Then another thing we can do is another thing we should do is we are going to set param underscore grid, and that's going to be equals to this parameter grid. Parameter underscore grid. Then the next thing you can do is you can say CV, which is going to be the value of cross validation, and that's going to be kf fold. I don't know why I named it that. Dot split. So what are we splitting? We are splitting x train underscore transformed, like that. So what other thing do we need to pass in? We need to pass in scoring. Scoring. How do we want to score? Now, scoring for grid search is going to be negative root mean squared error. And the reason is because mean squared error. The reason is because regression itself, that is this RMSE stuff, is a minimization problem. That is, we are trying to get the minimum RMSE that we can possibly get. However, grid search is set up in a way that it performs maximization. That is, it wants to go up. So what we now do is we trick it to feel like it is doing maximization just by adding negative to this, so that when it now returns the output, we can just give it we can just add minus, and it is going to fix it for us. So, but you only need to do this negative for any minimization thing that you're doing. Every other thing, in terms of maximization, that is in terms of classification, you don't need that. So if you want to see return train score, you can set that to true, but I really do not care about that. So that is going to just print out not only the test set but the train set also. So having done that, the next thing to do is to call grid underscore model dot fit. We're going to fit x underscore train underscore transformed. We're going to fit it with y underscore train. So, and how many models is going to get trained now? So grid search is going to use everything. That's what it does. It's going to use every combination of hyperparameter that is here. So this is how many? This is 1, 2, 3, 4, and this list should return 18 items. So let's check. If I say learn of this, learn of this, and paste this here, 19. Oh, it was 19 items. So we can do learn of this multiplied by 4. 1, 2, 3, 4. 19 times 4 multiplied by 5. Where did the 5 come from? The number of split. So we run that. So this grid search is going to fit 380 different models. It's going to fit 380 models, train 380 different models, and give us the one that returns the best set of hyperparameters that corresponds with the best score. So if we run it and everything is correct, then we see what happens. If not, we probably throw an error. It says max depth of 3. Well, that was quick. Oh, let's set verbose. That was really quick. Let's set verbose so that you can see. I'm actually interested in using how the whole thing train. So I can go verbose equals 3. Yeah, grid search should take verbose. Yeah, it does take verbose. So if I should rerun that, yeah, can you see? So that's higher training and it is done. And what you see now is all of this information here. So like we calculated earlier, it said it is fitting 76 candidates totaling to 380 fits like we calculated earlier. So we see each of the scores like this, each of the scores. Now we can go here and don't forget that our base model got up to 0.965. So and the lower the better. So let's see what the final model for grid search was able to do. So I'm going to grid model dot best score. Then we can multiply that by negative and we run that. So we have that does not look good. We were not even able to like outperform our base model, right? And if you look at it, then another thing is that on the base model, we did not really do cross validation. We're just looking at one split. Because if you check here, you are going to see that in some cases we got down up to 0.768. But even though we got down up to 0.768, if you look at all of these splits, because it's going to average it out, if you look at all of these splits like this, from here, this is where the split starts from. We see that there is actually a split that gave us 1.564, another one 1.1, then 0.768, 0.1. So if you average all of these things out, you are still at a high, a high value. So that is that. So we cannot like completely say that we didn't beat um the base model, because the base model is 0.96, but we wouldn't really know unless we actually do cross validation on the base model also, right? So let us come to this, and if we want to return this is what I mean. If you come here, we've already import cross val score. So if we take the base model like we did earlier, where is it? Yeah. So instead of just doing for a single instance, we can do cross val score, and we say estimator equals base model. Then we can do x equals x underscore train underscore transformed. Then we can go y underscore train, and we can go cv equals kfold dot split x underscore train underscore transformed. Then this one is y. What other thing do we need? That is all. I'm just going to call dot split. Oh, scoring. You see, scoring equals neg. You've seen this in the previous class on cross validation. Negative root means squared error. So we can just come here and say dot mean, because it's going to return an array. Then we can cancel out that one. Can you see? So you can. This is the true value of the RMSE for the base model. It is actually 1.3358, not this 0.6959. This 0.659 is just for a particular split, just one split of data. That is, if I should come here where we did x3 next test, y3 y test, if I should come here and change random state to 55, rerun this, and rerun this one again, you are going to see that, okay, rerun this again, and then rerun this one again. You see that this value of 0.965 is going to change drastically. Can you see it has changed 1.114? And why is that? Because we chose, just by splitting the data differently, from random state 23 to 55. So, and that's why we don't rely on something like that. That's why we need cross validation. So what gives us the true average strength of our prediction is actually what we see from this particular guy here, this cross validation. So 1.33. So the base score is 1.335, and our grid search, the lower the better. Our grid search was able to get that down to 1.123, like this. So if we come here now and check the model associated with the least score, for example, you can say grid and the hyperparameters is a grid underscore model dot best params. If we run that, so it says criterion of squared error and max depth of 3. That is what correlates with the best result, right? So if you want, you can actually expand this a lot. But the problem with research is that it is very slow, but it guarantees that within the range that you are searching, you are going to find the best one within that range, but it can be very, very, very slow. And there are, improvements, some algorithm that attempts to improve on the flaws of grid search, and we're going to be looking at those in the next class. So this is how you do grid search, and now that you have your hyperparameters, you can actually get grid underscore model. You can say grid underscore model dot best estimator, and this is the model. This particular one is the model. If you say model best grid model equals this. So if you use this to train now, you probably get out good outcome on your train and on your test, right? Better than what you had earlier. So that is what hyperparameter tuning means. So we can just take this, use it to predict. That is, we can come here, probably copy all of this from here and paste it here. Or you could just have a function for that if you want. Paste it here. And instead of base model, we're going to change it to best grid model. Control D, and that is all. The best grid model like this. Then we can call this one grid like this. So we run that. We have an error. It says best grid model is not defined because we haven't run this. And let's give this a spin again and see if it works. So can you see now, just by running that, we are on 1.0998, and that's just for uh, an instance. Like I always say, just for this instance of X train and Y train that we splitted at the top. So the true power of the model is when we actually do cross validation, which is what we see here. It is better than the base model, just a little bit. So in the next one, we're going to see how randomized search works, and we're also going to see how Bayesian optimization work with a library called Optuna. So see you guys in the next one. Thank you.